to run and things like that. So now that we've done all that, what we've created in our output directory, we've created all of these HDF5 files. These are the HDF5 files right there. And associated with each one is one of these XMF files. And what the XMF files are, they're small descriptor files that are metadata files that will tell a program like ParaView how to interpret the HDF file, because otherwise ParaView wouldn't know what to do with it. So when you open the files in ParaView, you always want to open the XMF files, because ParaView won't know what to do with just the raw HDF5 files. So I'll go ahead and, oops, let me get rid of that. Let's see, okay, so we'll open we'll just look at the this is the main solution file. Okay, so there's what we have. It doesn't look really exciting, but so by default you're going to get this is just the X displacement that we get. If you want to, you can see what the mesh looks like. But a lot of what you might want to do is operating things that involve vectors. And for this problem, we don't actually have vectors, but we can make them in ParaView using the calculator. So I'm going to make a vector here. I'm going to call it disvec, and I'm going to say displacement x times I hat plus displacement y times j hat. I don't know if I need a z. Okay. All right, so this 2D vector, and then we'll apply. And now, once I've done that, certain options become available to me. For instance, this one up here, that's where you can warp your solution by a vector. We'll try that. So we're going to warp it by the only vector we have, which is displacement vector. I'm going to do it by like 1,000. See what that does. And that just shows the, oops, fix that. It just shows how the displacement occurred as a result of our co-seismic slip. So we had, movement, you can see where the fault is, and then it's deformed it by whatever warping factor you put here. Another useful one for vectors is looking at glyphs of the solution. Here we're going to use arrows, and we'll just, you can set different properties for these things, but we'll go ahead and apply that. That's hard to see, so we'll color it by like a solid color that's like maybe black. And also, well, oh, that didn't work at all. Oh, that's really black up there. Okay. Okay, we'll make them yellow. Okay, and then also, like, the size, we might want to shrink it down a little bit, like, so that just shows what our yeah. So that's what we did with our co-seismic slip. We can also, if we want to, look at, I don't know if I want to do stresses right now, because should I? What's that? Wrap it up. Okay, so yeah, there's the fault, which we can see, but it's it's hard to see because it's kind of small. And it just shows what our slip distribution was. So if we, let's see, where's the, okay, and that just shows our X component of slip that we applied. So anyway, there's a lot more you can do with the visualization, but I think we might play with that either during Tinker Time or in one of the other demonstrations. So any questions? Yes.
So when you specified that it was left lateral slip, that presumably is what allows it to slip in that direction.
Yeah, the only options in 2D are left lateral or fault opening.
Left lateral is unique in 2D.
So it's always left lateral.
It's always, well, you can change the stuff. You can give it a negative value of left lateral and it becomes right lateral, which is, I think.
Oh yeah. Oh, is that what you meant? Yeah.
So
But
that's
this is not left lateral, but yeah. Yeah.
In 3D, if you have a fault that is warped, it'll pick the plane and then you have to actually look at the vectors that it's chosen to make sure, you know, which side did it, when you give it a normal, in 3D you give the fault like an up direction. And the up direction is normally 0, 0, 1. And it does the normal, it does up cross normal to define a horizontal tangential direction. Then it does normal cross that direction to get the up dip direction. And that uniquely defines all three directions. If you have a warp fault, you don't know where it sort of started, whether it was on this part of the fault or that part of the fault. And so sometimes it'll be sort of flipped, and so you may have to, your normal may be opposite of what you think it is. But PyLith will look at it and sort of develop the best unique orientation so that left lateral should always be left lateral, up dip should always, it's mainly the up dip, down dip that gets messed up. The lateral it can always uniquely define. If it flipped the normal, then you flip your reverse incline.
Yeah. I was going to just find a normal direction, but that's okay. I think maybe we better. What's now? Is it?
So the plan is tinker time until lunch. It gives you 45 minutes, not quite the hour and a half we hoped for. But you can, go eat your lunch and then come back in a windowless room and work, or you can. But the tinker time is sort of free for all. Make the best use of it that you can. Matt and I can do one-on-one, ask questions during lunch. You can ask questions. People always feel embarrassed to come up and disturb our lunch, but part of running the tutorial is we have made ourselves open and
we don't need to eat.
To whoever wants to answer questions. And then in the afternoon, I think we come back with meshing, more tinker time, and then green function. So lunch is 12 to 1.
Okay.